Parallel computing using CUDA revolutionizes data processing by enabling simultaneous execution of multiple tasks. CUDA, developed by NVIDIA, provides a programming interface for harnessing the power of GPUs. It introduces concepts like blocks and threads, allowing efficient task distribution. Understanding shared memory and asynchronous operations is crucial for optimizing performance. This session explores these concepts, aiming to enhance computational efficiency. CUDA, or Compute Unified Device Architecture, is a parallel computing platform and application programming interface model created by NVIDIA. It enables developers to use a CUDA-enabled graphics processing unit, GPU, for general-purpose processing. Key concepts include blocks, threads, and shared memory, which facilitate efficient parallel execution. Understanding these elements is crucial for optimizing performance in parallel computing tasks. In heterogeneous computing, combining threads and blocks optimizes performance. Blocks contain multiple threads, each executing tasks concurrently. Indexing helps in accessing data efficiently, while shared memory allows threads to communicate. The e.g. syncthreads function synchronizes threads within a block. Asynchronous operations enhance device management, and error handling ensures robust execution. These concepts are crucial for efficient parallel computing. Parallel vector addition can be optimized by using both blocks and threads. Initially, we explored using many blocks with one thread each and one block with many threads. Now let's adapt this to leverage both blocks and threads for efficient data indexing in CUDA. To index arrays using both blocks and threads, calculate the unique index with int index equals thread_index.x plus block_index.x times m. This formula accounts for m threads per block, ensuring each thread accesses a distinct array element. This method is crucial for efficient parallel processing in CUDA, especially when handling large datasets. To determine which thread operates on a specific element, calculate the index using the formula int index equals thread_index.x plus block_index.x times m. For example, with thread_index x equals 5, block_index x equals 2, and m equals 8, the index is 21. This index identifies the thread responsible for the red element in the array. To optimize the main function, replace the hard-coded value with blockdim.x for threads per block. Update the index calculation to use blockdim.x, ensuring efficient parallel execution. The add function should utilize parallel threads and blocks, computing kindex as the sum of a index and b index using the updated index formula. In this section, we define constants for vector size and threads per block. Allocate memory for host and device arrays, and initialize input values. Transfer data to the graphics processing unit, execute the kernel with specified blocks and threads, and retrieve results back to the host. Finally, clean up allocated memory to ensure efficient resource management. To handle arbitrary vector sizes, update the kernel launch to add n plus m minus 1 divided by m da db dcn. This ensures all elements are processed, even if n isn't a multiple of blockdim.x. Use an index check within the kernel to prevent accessing beyond array bounds, ensuring safe operations. Launching parallel kernels involves using add to execute n copies of the add function. Utilize block_index.x for block indexing and thread_index.x for thread indexing within each block. Allocate elements to threads with int index equals thread_index.x plus block_index.x times blockdim.x, ensuring efficient parallel processing in Compute Unified Device Architecture. In heterogeneous computing, threads within a block cooperate using shared memory and synchronization. Use synththreads to ensure all threads reach a barrier before proceeding. This prevents race conditions in asynchronous operations. Proper indexing with block and thread indices is crucial for efficient memory access. Error handling and device management are essential for robust CUDA applications. Applying a 1D stencil to a 1D array involves each thread processing one output element with block dim x elements per block. For a radius of 3, each output element is the sum of 7 input elements, requiring each input element to be read 7 times. This approach efficiently utilizes shared memory within a block. Within a block, threads can share data using shared memory, which is extremely fast on-chip memory managed by the user. Declared with shared, it is allocated per block and not visible to threads in other blocks. This allows efficient data sharing and reduces global memory access, enhancing performance in compute unified device architecture applications. Cache data in shared memory by reading blockdim.x plus 2 times radius, input elements from global memory, compute blockdim.x output elements, and write them back to global memory. Each block requires a halo of radius elements at its boundaries, ensuring efficient data processing with halos on both left and right sides. In the Stencil 1D kernel, shared memory is utilized to store input elements. Each thread reads its corresponding element into shared memory, with boundary threads handling halo elements. This setup ensures efficient data access for subsequent computations, minimizing global memory access latency. The Stencil kernel applies a computation pattern by iterating over a range defined by the radius. Each thread calculates a result by summing values from shared memory stored in temp using offsets. The final result is then written to the global memory at out open bracket gindex close bracket. This approach optimizes data access and computation efficiency in CUDA programming. The Stencil example can fail due to data races. If thread 15 reads the halo before thread 0 fetches it, inconsistencies occur. For instance, temp lindex is set from ingindex, but if thread x is less than radius, it fetches additional data. This can lead to incorrect results, as seen when storing at temp 18 and loading from temp 19. Synchthreads is crucial for synchronizing threads within a block, preventing read after write, write after read, and write after write hazards. It ensures all threads reach a barrier, maintaining data integrity. In conditional code, the condition must be uniform across the block to avoid deadlocks. This function is essential for efficient parallel processing in compute unified device architecture. In the Stencil kernel, shared memory is used to store input elements, ensuring efficient data access. Each thread calculates its global and local indices, loading data into shared memory. Synchronization with Bratz's char synchthreads ensures data consistency. The Stencil operation sums values within a defined radius, storing results in the output array. Launching parallel threads involves using kernel to initiate n blocks with million threads each, access block and thread indices with blockidex.x and threadidex.x, allocate elements using inti-index equals threadidex.x plus blockidex.x times blockdim.x, declare shared memory with shared hawks, visible only within a block, use synchthreads to prevent data hazards. Managing devices in heterogeneous computing involves understanding blocks, threads, and indexing. Shared memory, declared with _shared _ allows data sharing within a block. Use synchthreads to prevent data hazards. Asynchronous operations require careful error handling to ensure efficient device management. Kernel launches in compute unified device architecture are asynchronous, allowing control to return to the central processing unit immediately. To ensure data integrity, the central processing unit must synchronize before consuming results. Use CUDA MMCPY to block the central processing unit until data transfer completes, or CUDA MMCPY async for non-blocking transfers. CUDA device synchronize ensures all preceding compute unified device architecture calls are complete before proceeding. All CUDA API calls return an error code, CUDA error T, indicating issues in the API call or earlier asynchronous operations. Use CUDA getLastError to retrieve the last error code. To understand the error, convert it to a descriptive string with CUDA getErrorString CUDA_error.t and print it using printf. This ensures effective error handling in CUDA applications. Applications can query and select GPUs using CUDA get device count and CUDA set device. Multiple threads can share a device, while a single thread can manage multiple devices. Use CUDA set device to select the current device and CUDA mem CPY for peer-to-peer copies. Retrieve device properties with CUDA get device properties for efficient management. We've explored writing and launching CUDA C++ kernels using double_global_, block index X, and thread index X. We've managed GPU memory with CUDA malloc, CUDA mem CPY, and CUDA free. Additionally, we've handled communication and synchronization using shared DRIs, syncthreads, and compared CUDA mem CPY with CUDA mem CPY async alongside CUDA device synchronize. The compute capability of a device defines its architecture, including registers, memory sizes, and features. Focusing on Fermi devices with compute capability 2.0, they offer caches, fused multiply add, 3D grids, and more. These features enhance performance and flexibility, crucial for advanced compute unified device architecture applications. Refer to the Compute Unified Device Architecture C Programming Guide for a comprehensive feature list. A kernel in CUDA is launched as a grid of blocks, each containing threads. These are identified using built-in variables, threadix, blockix, blockdim, and griddim. While typically visualized in one dimension, these indices are inherently three-dimensional, allowing for complex data manipulation and parallel processing across multiple dimensions. Textures in CUDA are read-only objects with dedicated cache and filtering hardware supporting linear, bilinear, and trilinear filtering. They can be addressed in one-dimensional, two-dimensional, or three-dimensional, with out-of-bounds handling options like wrap and clamp, ensuring efficient and flexible data access. Thank you for your attention. We hope this presentation has enhanced your understanding and sparked further interest in the topic of parallel programming with CUDA.